not this x, okay? Let me fix my computer so this won't happen. So what I'm going to do is I'm going to expand it so manually so that I don't make that x disappear.
Do you have to hit import?
What?
Import? I was just wondering if you have to hit it.
For advanced thermodynamics.
What?
Bottom.
No.
Oh, okay.
No.
Just hit it, see what happens.
No. So click X. No, it didn't give me a warning. Normally it gives me a warning if it doesn't like. Should have given a warning, but it didn't give a warning that it doesn't like the water. Anyway, this stands for number components to Peng-Robinson. Okay? So we're done with the preliminaries. Click Enter Simulation Environment. Let's expand this. And I think it expanded okay this time. You see your palette here? This is the things you can do. What I was talking about, the criticism of the HYSYS interface, new interface, is you see here the reactors, CSTR, plug flow reactor, and here are the general reactors. Okay, so all the reactors are grouped together. The new interface of HYSYS has everything together except some that says columns. And columns, it has the distillation columns, liquid extraction columns, and the conversion reactors. No logic, but that's what it is. All right. Is everybody in this screen? We go back to the previous screen by pressing the beaker. Learn how to communicate between the two screens. And by the way, the beaker also exists in HYSYS and in Aspen now. Okay, we're back here. We can go to the components. You can view components, component list 1. Actually, we can look some information for every component. Click View. If you click a component nitrogen and View Component, this will pertain to your first homework. You see here several tags, the ID. If you click under critical, you find the molecular weight, the normal boiling point, ideal liquid gas density. More important, you find critical temperature, critical pressure, critical volume, and eccentricity, which is the eccentric factor that comes into the equation of state models. We're going to be using that in this class. So you find, okay, now that temperature dependence. You find the temperature dependence of ideal gas enthalpy. And you can see here the equation that is being used. Typically it goes until E or F, and you see here the coefficients, and eventually they become 0. So in this case, for nitrogen, you can see you have A, B, C, and come on, scroll down. Yeah. It goes until F. What does this mean? These are the coefficients of how the mass heat capacity, this is an equation for kilojoules per kilogram. So it's mass, not molar. So that's the H hat in class notation. Okay? Kilojoules per kilogram, or same thing, joules per gram. And you see here the coefficients. So for nitrogen, H hat according to this would be 2.886, excuse me, plus the B coefficient times T, Ct squared, and so on. Okay? Question, yes?
Oh, what do the coefficients mean?
They're polynomial fit.
Nothing?
No,
Okay.
it's a polynomial fit. It's a mathematical expression that fits experimental data. You have experimental data and you fit it to polynomial expression. That's all there is. Okay? All right. I'm talking about that because I have in your homework say that one of those coefficients maybe is not correct. The software has some bugs, guys. And one of the bugs is that as you will discover in doing your homework, one of those coefficients is not correct. The others are fine. It's a riskier value that is not being used internally. All right. So let me go back. How do I go back? X from this and return to simulation value. Okay, we have this palette. If you lose it, or if you want to remove it, F4 toggles it in and out. Okay, function 4, F4. At the very top, you see two arrows, blue and red. These are the material streams. Something else we should be doing also. We can choose what units we're going to be using. SI or engineering units. Actually, it's not exactly engineering units, it's oil field units. If you go to tools, let's fix the units first. Probably you all have the correct units if you just installed it. You probably have SI units, but I'm not sure what units I have, so let's go. So go to tools, and you see here preferences. If someone stays behind, raise a hand and tell me, oh, I don't want to lose anybody. Everybody with me? All right. So click preferences. And by the way, while we're here, under simulation, activate property correlations. Always have this active. Okay? Click variables. Here are your units. So SI, I just under SI units. Field units are engineering units with one exception. Most flows, what are the units that we have for flows? Oh, that's not what it normally has. What the? Did I fix mine? Okay, liquid volume flow, that's what I meant to say, sorry. Look at liquid volume flow. What are the units? Barrel per day. That's not your normal engineering unit. That's the unit for oil, right? But you can create your own units. You can replace that and name it engineering. Okay, make it gallons per minute or whatever you want to use as units. So you can make your own units and save it and have that. Anyway, we want SI units for this exercise. I gave you everything in SI units, right? 500 degrees C, we have C, we have kilopascals pressure. Yes, Josh?
What was the box that you checked on the previous screen? Did you check a box on the previous simulation?
Yes, I checked in the previous screen, simulation, activate property correlations. Okay, so we have SI units, so let's exit that X again. And now let's create that process, the diagram I have there. What will I have? I'll have a material stream, so click on the blue arrow, and then move the cursor wherever you want it, and click again. And double click on it. We can name it. I guess 1 is a good name for it, since I put 1 and 2 there, but yeah, I'll call it stream 1. What do you think we have at vapor fraction at the 8,500 degrees C, 80 atmosphere nitrogen? What do you think it will be? Vapor or liquid?
That's a high pressure.
500 degrees C, you think it will be liquid? 80 atmospheres is high pressure, but not that high.
I mean, it is nitrogen.
Probably it will be vapor, yeah. I expect it to be vapor. It's at a high temperature. To have liquid nitrogen, you have to be very cold. So it will be vapor. So should I put 1 vapor? I can put 1 vapor. And my temperature is 8,000, 500 degrees C. Put the temperature. And I want to put now, wait a minute, that shouldn't have happened. Okay, because it's not possible? All right.
What did you do? Okay, where'd you get the 1? You just said.
I put 1, but I wanted to show you something. I expected something else to happen, but I guess because it's sort of question, I shouldn't be able to put the pressure here. Let me see what happens if I put the pressure.
It took it from me.
It shouldn't take it. Something is wrong here. Let me delete this. Oh, I didn't put composition. That's why. Okay, hold it. Before we do any of this here, let me delete everything. I forgot to put composition. You can put composition anytime, but to show you what I want to show you, I have to put first composition. That's why. If I have multi-components, we would have taken it. What's our composition? Pure nitrogen. So type 1 for mole fractions. Okay, so back again because I didn't do things organized. Okay, so everybody put the stream in, right? You put an arrow, you put the stream in, come on, click the blue, put the stream in, double click on it, change the name, whatever you want, right? Everybody's here? Okay, I'll delete this and I'll continue where I was. Yes, I want to do it. Okay, so we are here. Now, you enter things under conditions and composition. Let's first enter composition. We're going to have pure nitrogen. Put under it's mole fractions. You can change the composition to be mole fractions, mass fractions, liquid volume fractions, or flows, molar, mass, or liquid volume flows. So you can provide the composition any of these with different ways. I'll leave it at mole fractions, and of course pure nitrogen I'll put 1. The moment I press enter, another screen pops up. It has the default, it has what I gave for nitrogen, the rest are empty. Empty is equivalent to 0. I'm done with this. But this screen has an OK. Instead of the X, I'm pressing OK. If you see an OK, you press OK to exit the screen. If you don't see an OK, you press the X. All right? Click OK. Now let's go to conditions. Let me put, there is going to be vapor, and put 1 on vapor. Let me put the temperature. What's going on? It's trying to find the pressure and cannot find the pressure. Okay. First important Unisim HYSYS Aspen lesson. If you specify a vapor fraction, you are actually specifying 2 phases in equilibrium. The moment that I put 1 there, what I did is I specified I have saturated vapor. I didn't specify I have gas. I specified I have saturated gas. Which means I have 2 phases in equilibrium. If you have 2 phases in equilibrium, how many degrees of freedom do you have? Only 1. You cannot specify both pressure and temperature. Now, my temperature is too high to have 2 phases in equilibrium. And it cannot find an equilibrium pressure. That's why it's complaining. Let me reduce the temperature to something, I don't know, like minus 100 degrees C. We'll go back to the condition we have, but let me show you this. So let me change this for 500 minus 100 degrees C. Still too high. Okay, let me make it minus 200 degrees C. As I told you, it's definitely gas. There we go. At minus 200 degrees C, notice it calculated the pressure. You don't have the degree of freedom to specify both temperature and pressure. To specify temperature, you have the pressure. To specify pressure, you have the temperature mechanical. And because the same component, no matter what I change the fraction, within some slight numerical inaccuracies, you will see the calculated pressure will not change. So I put here 1, let me change to 0.8. What's the pressure? Stayed at 60. I put 0.2. Pressure stays at 6. I put 0, pure liquid. It's liquid in equilibrium vapor. Oh, what did I do? I put the 0 on the temperature. Minus 200. Okay. I put 0. Pure liquid. It's liquid at equilibrium with vapor. It's saturated liquid. Okay? So, notice also something else. What I enter is in blue. What it calculates is in black. So in this case, do I have saturated vapor? No. Don't enter a vapor fraction unless you have saturated vapor. Clear? All right. So I will delete the 0 and allow enter my conditions. And then you see it will become 1, but black. 1 black, if it calculates it, it doesn't mean saturated. If I enter it, it means saturated. So delete this. Let's put our real temperature 500 degrees C. And let's enter the 8,000 kilopascals. Now I can enter, because I don't have any more saturated, now I have 2 degrees of freedom. I can specify both temperature and pressure. And you can see it calculates, yes, I have pure vapor. Okay, it's superheated vapor. It's not saturated. Question, Brian?
It's stopped working for me. Like it
It
isn't
doesn't
filling out
calculate.
information.
It doesn't calculate the pressure for this.
So when I had
Did you specify the composition?
yes.
Okay. Do you have a red light? Okay, press green light. Yeah. All right.
Green light.
Okay.
Important.
All right, since Brian tested something, a very important thing about Unisim and HYSYS is that, like Excel, it continually recalculates. And you see on top here, green and red light. If it's green light, it means it's continually recalculating. If you press red light, it stops the continuous recalculation. In your design class, you're going to be using the red light a lot. Behind all this software, we are solving systems of nonlinear algebraic equations. Lots of equations. What should you have learned in COT? You should have learned that, yes, and hopefully I taught it to you, Brian. You should have learned in COT that if I have good initial guesses, I can converge very fast to the solution of system of nonlinear algebraic equations, for example, using the Newton-Raphson method. So if you have good initial guesses, you converge very fast and easily. So the key to get, in your design class, you'll be fighting to converge nasty columns. The key to success there is to get them to converge anywhere. It's easy to converge them in certain states than in others. And then, to very slowly move to the conditions of the column from where you are to where you want to be. And what you do is you push red light to avoid recalculation when you make changes. Because when you press red light, you save the internal variables. Let's say I want to change from one stream to the other. If I have the green light on, the moment I remove the one stream, before I replace it with the other, it will immediately recalculate. And you'll totally destroy your converged values. If you press red light, remove the stream, put the new stream in, which is probably similar to the one you took out, press the green light, then you're fine. Because you made a small change, and a lot of things we'll be doing in the design class will involve small changes, you'll be fine. Sometimes if you have a problem, red light pops up. So one of the first things, if yours is not running, is check if by any chance the red light comes on. Okay? But that's the business of the red-green light. Okay. So I entered those two, calculated. Notice immediately calculated a couple of other things. It calculated the molar enthalpy. Now that's molar enthalpy. Okay? How many degrees of freedom? I have 2. Remember state variables. You specify any 2, all 8 are specified. Okay? So, it has here enthalpy and entropy. It's also specified Helmholtz, Gibbs, and we have temperature, pressure, H, S. U is also specified, whatever I'm forgetting. S, H, U, Helmholtz, Gibbs. No, we have 5 here. Oh, molar volume. Okay, so specifying molar volume.